All right, so good afternoon. We're going to go a little bit further in chapter 3 today. Today we will look at this topic. Oops. Now, I already introduced this yesterday, and I just introduced it. So we'll kind of do an overview and we'll practice this today. And I'll introduce the last section we're going to do. And that's it. Shouldn't take us too long. The valence shell electron pair repulsion is a theory that is based around the fact that negative charges, electrons, they will repel other electrons. So when you have an actual physical real molecule in three-dimensional space, in the universe, not on a piece of paper, the bonds, the electrons, the other atoms will try and separate or spread as far apart as possible. Now, again, we don't need to get too caught up into why or how this happens. We just need to know how to predict the three-dimensional shape of this molecule. And there is a reason for this. That I'll get to tomorrow, which will definitely mean a lot to some of the chemical engineering students, for example. But all we need to do as a group is to be able to draw the electron dot diagram and study the central atom. We look at the number of lone pairs and bonding groups or bonds that there are. You count the bonds as one thing. I guess that's not clear. What I mean is a bonding group can be a single bond. It can be a double bond. A double bond is not two bonds. It is a double bond. And we can have, of course, triple bonds. You won't see a lot of triple bonds in this course, but you will definitely see some single and double bonds. But the key there, and I'm going to practice this with you today, is don't count doubles as two single bonds. It's its own thing. It's just called a double bond, and you'll see this today. So in order to do this, we need to go to the data booklet and use the information on that data book, or in that data book, I should say. It's around in the middle. I can't remember the page number, but it's around the middle of your data booklet. You have this page. And really all we need to know is the bonding and lone pairs. These tell us the name of the shape and the appearance of the shape. Now, one thing I'll mention before I get into the examples is think about this course and this time where your next quiz, for example, your next test, not quiz, your next test, it'll be online. It won't be until like the end of November, so you don't have to worry about it. But you can't draw on D2L, not yet anyways. So it's really important that you guys are able to pick the name of the shape out of the list for multiple choice reasons, because again, on D2L, we cannot draw these shapes. So the drawing, the appearance will be important if your final exam is on campus. We're going to practice this today, but make sure you know the name as well. So now, again, you don't have to memorize this. You just have to know how to pick it out from a list. So your challenge, really your only challenge, is can you figure this part out? Once you know that part, that column, the bonds and the lone pairs, the rest is easy. So let's do this. Now, I'm going to quickly go through this one because I want to show you these examples here. I want to actually practice them with you. So let's just look at this example. This shape. This shape, you might have an easier time if you drew it simplified. If you just said, okay, well, we have silicon bonded to 4 fluorines. This is not a shape. This is not an answer to anything. This is just a way you can kind of think about the molecule. This is the electron dot formula. you definitely need to know how to make electron dot formulas. But when I'm looking at this formula, I know that this compound has 4 bonds. Whoa, my pen didn't like that. And 0 lone pairs. And again, I know a lot of you might be thinking, well, there's a million lone pairs in this, but not on the central atom. I do not care about these lone pairs. They don't tell me the shape. Okay, all I care about is what's happening with the silicon in the middle, and it has 4 bonds, no unbonded electrons. So I go to my data booklet, I find it on the list. I know the name of the shape is tetrahedral. That's a mathematical 3-dimensional shape, kind of like a pyramid. And then I have my sketch. This is like my rough draft or my skeleton. I'll fill in the blanks, meaning wherever I see an A, I'll put the central atom, and then the other guys go around on the outside. So again, I'm going a little quick because I want to actually do some with you, but using my data booklet, that's the shape my data booklet tells me. So wherever I see A, I put in an S. Wherever I see X, I put in F, and that's my molecule. All right, again, I'm going to practice this with you. I know this is a little maybe fast, but there's really no point unless I can show you some myself. Let me just check the chat here. Yeah, it's not too bad. I don't find it that bad. And Aman and everybody else, when you actually see me do some of these examples, it will be quite easy. So this is you guys can check this out on your own time if you want. I typically use moleview.org. If you did want to see the shapes in 3 dimensions, if you wanted to like you can kind of like play around with it. I don't think it works very well on your phone, but it will work well on a desktop or laptop. And you can make little shapes and kind of see how they look. But the whole point of this class today is, what if we are on a test or we don't have a computer, how do you do this with the data booklet? And it's really, really straightforward. There's one thing I want to mention about the data booklet in a second. I guess I do have this example here as well. So let's look at this one. This is the Lewis dot, or I say Lewis dot, that's just because I'm an old man. I mean electron dot, it's the same thing. I have the electron dot formula for ammonium and H3. And I notice I have 3 bonds. Okay. I notice I have 1 lone pair. So I would go to my data booklet. How do I want to do this? I'll share a new screen. So I'm going to share a new screen here. I'll share my data booklet with you, which of course I closed. Hold on, guys. Let me get my data booklet open. I closed it from the last class. I didn't mean to do that. Okay, perfect. Okay, so new share my screen. I'm reading my data booklet now, and I'm looking for the correct bonds and lone pair. I'm here, okay? So I go down, I'm looking for 3 bonds and 1 lone pair. 3 bonds and 1 lone pair. Oh, here it is. So the name of my shape is called trigonal pyramidal. Again, you don't need to memorize this. You just need to know how to find it in a list. And here's my shape. Okay, for the A, I would put in the N. For the X's, I would put in the H's, and there would be my shape. Now, it's really important when you do your shape, I'll go back to my PowerPoint, you do have to include your lone pairs. So again, the data booklet says that we would draw it like this. A being the central atom, X being your extra atoms. I guess you can think of that like X being extra. And then up top, we have E. Always include your lone pairs. And you, if you wanted to, you could also call this E. I don't care. I personally, I like the dots, but it doesn't matter. As long as you show me that at the top of this molecule, there are electrons, that's so important because these electrons are what's pushing these other bonds away from it. And that might not seem important, but it's part of the reason why some elements or, sorry, molecules are polar and some are not. Okay, let's just do some examples. I mean, again, I know I went a little quick through those two, but it's a lot better if me and you can do it from scratch. There is one thing I'll mention to you though, some good news. There are other shapes that exist. And if you look in your data booklet, you'll see them. But we do not use these shapes in this chemistry course. The reason they're in your data booklet is because your data booklet is for all chemistry courses. So some courses, some maybe people in different programs use different parts of the data booklet. So let me explain to you what I mean there. I'll answer your question in a second, Aman. That's a really good question, actually. The question is about the bond angles, but I'll get to that in a minute. So if I actually zoom out in the data booklet, look at the page, right? The page is huge. In Chemistry 1120, we only worry about the top half. We do not worry about these. Now, that will not be an issue. Like, you don't need to memorize this because you will never see in Chemistry 1120 any of these numbers. You just won't see it. Like, it's never going to happen. So you don't need to memorize this. That, like, what I mean is, you don't need to memorize that you're not going to use the bottom part of the table. Typically, when I teach this in class, I see the students grab their data booklets and scratch out the bottom of the table like crazy people. You don't need to do that. The only numbers you'll get will be from here, from the top part. Okay, let's practice this, and I will answer Aman's question as well. Aman's question was, do you need to calculate the bond angles? And the answer is no. This is really good information, but you won't need to calculate them or anything like that. Okay, you won't need to worry about bond angles. Okay, all you need is shape and appearance. So let's do it. Let's work at some together. This will make more sense when I actually do some of these examples. Okay, some of you who have your notes printed, you'll notice that this is changed. It was BF3. I've changed it to PF3. That was like a little mistake there. So PF3. If you have your notes printed, just change the P, or the B, sorry, to a P. Phosphorus. Okay, let's take our time now. I can slow down. Let's look at these together. It's a lot easier than it sounds. Step number 1, draw your electron dot formula. Now, we are technically professionals at this point. You guys have been drawing electron dots for a week or so now. Well, I mean, in class at least, we've been doing them. So, well, first, let me just do a sketch. I'm going to erase this in a minute. This is why it's good to have, a piece of scrap paper when you're doing an assignment or something, like a little notebook next to you. Because if you think about this puzzle, oxygen is in group 16, 6 electrons. Hydrogen is in group 1, 1 electron. Think about this puzzle. There's really only one possible way for this puzzle to go together. The single electrons will bond together to fulfill the octet rule. And we know hydrogen is so small, we don't need to worry about the octet rule for hydrogen. So my molecule, when I put it all together, will look like this. It would be definitely in your advantage to look at this. Or sorry, I got distracted because somebody was writing me something. It would be in your advantage to know how to draw things like water, because water is such a common chemical. Okay, so anyways, there's water. I'm going to get rid of my sketch on the right side. The sketch is just, again, something you would do on a piece of scrap paper if you weren't sure how to do this. Okay, next step. Only looking at my central atom. So the central atom is the atom that everything else is bonded to. I have on that central atom 2 lone pairs. On my central atom, I also have 2 bonds. So I'm going to go, excuse me, go to my data booklet and hopefully not choke on my tea. I'm going to go to my data booklet. Sorry, somebody just had the answer in the chat. 2 bonds, 2 lone pairs, you're correct. I'm going to go to my data booklet. Clear my drawing here. And I'm going to find which one of these elements or molecules has 2 bonds and 2 lone pairs. Well, there's only one. This guy, right at the bottom. So a molecule that has a central atom that has 2 bonds and 2 lone pairs, we would say that it is bent. That's one of the really important physical properties of water, is that it's a bent molecule. And I have a little template for my sketch here. So I'm going to take that template, my little cheat sheet, my little guide, and I'm going to write it next to my molecule. Now, you do not need to do this part on a test, but I just want to show you how I go from one answer to the other. So my data book is saying that the molecule should look like this. We have we have a wedge with electrons, we have hashes with electrons, and then we have our 2 elements or 2 bonded atoms down bottom. So all I do is change the letters. So instead of A, I'm going to call it oxygen. Instead of X, I will put my hydrogens, and then I'll just put my electrons here. The wedge, this is called a wedge, which I'm attempting to draw, and these are like hashes or dashes. These show you that the molecule is in 3 dimensions. Well, I mean, everything is in 3 dimensions, but I just mean it shows you kind of the 3-dimensional layout of this molecule. You are more than welcome on a test, or I guess it would be on your final exam, if you wanted to put E there, that's fine as well. I don't care. It all means the same thing. I prefer, the chemist in me, or chemistry teacher in me, prefers that. Okay, let me show you one more, and then I'm going to get you guys to try 2, and we're pretty much done. I'm just going to introduce the next section, and that's it. So I want to do this one. P is in group 5. So, oops, well, okay, group 5 looks like this. Group 5, group 15, it would have 5 valence electrons. And fluorine looks like this with 7 electrons. Okay, I'm really gonna throw my pen out the window someday. So think about it. What that means is every F will bond, because every F needs 1 electron, and it will bond to the phosphorus like this. Now, notice I'm drawing my lone pair, or the electrons, the lone pairs around my fluorine nice and small. They don't matter for the shape. They have nothing to do with the shape. For the shape, all I do is look at my central atom. Okay, I don't care about the fluorines. The fluorines don't control the shape. So we have, oops, hold on. I did not mean that. I also didn't mean that. I'm having pen problems here. Let me just, I want to clean this up because I liked how it looked. Okay, there we go. Now pen, orange, there we go. So I have one lone pair. Okay, I know it's a lone pair because it's not bonded to anything. There's no other atom up there. And then I have 1, 2, 3 bonds. So I go to my data booklet. Oh, let me check the chat before I go to the data booklet. Let's see what people are saying. Oh yeah, my pen is a big problem. I don't know how to fix it. It's driving me crazy. And Aman in the chat, you're on to the next question. If you have 2 double bonds like CO, the total bonds will be 2. Double bonds and triple bonds only count as 1 bond. Like, again, I mentioned this before. It's a double bond is not 2 single bonds. A double bond is a double bond. So if you had a double or triple bond, don't count them in, like, don't count each line or each little bond in that double or triple. It's counted as a bond. And you guys will see this in the next example. So let me get my answer up and give you guys a chance to try the next 2. Oh, sorry, let's look at the data booklet. I'm looking for, clear this. I'm looking for something that has 3 bonds and 1 lone pair. There it is. Maybe my favorite shape, trigonal pyramidal. You don't need to memorize that word. You just need to know how to pick it out of a list. And here is my sketch. All right, so going back to my notes, the data booklet says it will look like this. E, and then X, X, X. All right, so put it all together, put in your elements. So I have P, F, 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 and then up top, you put your alone pairs or your electrons. Again, I prefer the 2 dots, but completely up to you. All right, so with that said, I would like to give you guys a couple of minutes to try these 2. Now, let me just leave that up for a second if anybody wants to take another look at it. But I would love for you guys to try the next 2 on the next page. All right. Well, maybe I can do this. On the next page, guys, I'm going to leave my notes up. But on the next page, you have CO2 and DCH4. Now, I know you guys, like, I know you can draw on my screen, but really, if you guys want to check your answers with me in the next 2 minutes, all you have to do is type the name of the shape in the chat. If you can type the name of the shape, linear, bent, tetrahedral, trigonal planar, trigonal pyramidal, if you can type the correct name of the shape, then I'll know you have it correct. So try these 2, C and D, and I'll be back in 2 minutes. All right, 2 minutes. Okay, so I have a lot of good answers in the chat. Well, I mean, I think you guys are lucky because my other class, I had a lot of wrong answers, but in the chat, I'm getting a lot of good answers or correct answers. I'm very happy, very impressed with that. So maybe I did a better job with you guys. So let's look at this, look at your answers, and then we are almost done. All I want to do, especially because there's no class on Thursday, I just want to introduce this section so we can kind of tackle it tomorrow. So just maybe 10 minutes or so and we'll be out of here. Let's look at these answers. Okay, guys, we've drawn these two chemicals a million times. So I'm going to very quickly sketch them. Carbon dioxide, we've drawn in this course at least two other times, looks like this. Carbon dioxide, and this is kind of what Iman was talking about, carbon dioxide has two double bonds. Now, like in the past, I would get students that would look at this molecule and the students would say, oh, okay, well, there's two double bonds. So that means there's four bonds, no lone pairs. This is tetrahedral. How could this be tetrahedral, right? Like there's no way that I could make this shape with this structure. There's no way. Like I only have two oxygens. Where would they go, right? It doesn't make sense. So the answer is it doesn't have four bonds, it has two. So I'm looking at the central atom. I have, oops, I did the same thing again. My bad. I have two bonds and I have no lone pairs. Now again, I'm only looking at the central atom. I don't care about the lone pairs on the oxygen. The double bonds are just one type of bond. So I have two of them, two double bonds. All right. So that means I go to my old trusty data booklet. I find 2 and 2. Sorry, 2 and 0, not 2 and 2. I got water on the brain. I find 2 and 0. And doesn't this appearance already look like the molecule we have sketched? Right? Look at it. It looks almost the exact same. So one thing to mention here is that the data booklet is saying it's XAX in that lineup, and that's fine. But just remember, when I then sketch my molecule, oh, I'm sorry, I'm going to write these double bonds, or these bonds as double bonds. Okay, so it would look like this. You could put the electrons in if you want. Sorry about my dog there. But all you need to know is that this is linear. All right, just give me 1 second here. Hold on. All right, I am back. Everything's good. So yeah, I mean, again, what I mentioned is if I just want you to draw the shape, you don't need to worry about anything except that. All right, but if you want to be perfect, you could definitely throw in the lone pairs on the oxygen, but it's up to you. I'm just looking for that nice, simple, linear shape. And again, I had like a student in the earlier class say, well, wait a minute, why are you writing that as a double bond? It's in the data booklet, this just represents a bond. It could be a double, it could be a triple, it could be a single. So you definitely, for full marks, you need to put in the double bond here. Okay, cool. All right, the last one, the most common one that you would probably see. I mean, we've drawn this one probably 4 times since we started. It's methane or methane if you're British. Well, I shouldn't say if you're British, but depending on where you are in the world, people say words differently. Like I know people in the UK would say aluminium, and people in North America would say aluminum. So we say methane, they say methane. It's all the same thing. This is actually one of my favorites. It's honestly one of the easiest ones because like there's really nothing to distract you here. There's no crazy lone pairs on the hydrogens. I mean, really, this one is so simple. It's just, oops, that's like the third time I did that. That's me writing with my highlighter, not writing with my pen. Sorry, I have 4 bonds and no lone pairs. So by the way, guys, this shape up top is called linear. This shape we would call, it's in your data booklet. I'm just going to sketch it because, I know what it looks like. This shape is called tetrahedral. So my molecule would just look like this: C, H, H. You don't have to be an artist. I am certainly no artist. CH4. There you go. That's it. Cool. Now, we're not done with this yet. So if anybody in here is still a little nervous about this, or you still don't quite get it, we will be looking at more examples before we finish chapter 3. So guys, it's 3:09. If you just give me 3 minutes, I'll be done. I want to set us up for tomorrow, and plus I want to get you guys on the same page as my other class. So just give me 3 more minutes and you're out of here. I just, like I said, want to introduce this next class, or this next section. And I got a message in the chat. Just give me 1 second here. I'll read that. Oh yeah, sorry about the monster, my dog. Yes, I don't know why. I know what's going on is when people are in the hallway. None of this happens. I'll tell you. I'll do a quick detour here with the dog. I've had her for months, and I'm fostering, so it's not mine. I'm kind of hoping she'll be adopted someday. I'm fostering this dog, and I had her since June, and she never made a peep all summer. But I live in an apartment building, and somebody in my apartment building got another dog. And the minute that dog showed up on my floor, my dog started going crazy. It's like every time she hears something, she thinks it's the other dog. She's, I don't know, weird. It's so strange. I think she's like protective or something. But anyways, it's not really a big deal. The other people can't hear it. It's only you guys can hear it. And I'm working on it, trying to figure out how to get her to not bark at other dogs. She doesn't bark at humans, only other dogs. Yeah, I know a lot. So Mohammed, I work with a lot of other, like where I live with basically everybody I work with. And a lot of my friends have cats or dogs or things like that. So anyways, it's interesting. All right, so let's I just want to introduce this and we're done. I just have 2 things I want to say. This is a section about the intermolecular forces. This is such an important section for engineering, maybe medical science, but definitely the engineers in here, especially the chemical engineers. This is such an important topic. This is like where the hydrocarbon, petroleum, chemistry comes in. This is all that we talk about is intermolecular forces. So this is a really important section, and it should only take us a class or 2. So we're going to look at all of this, but all I want to do today is tell you 2 definitions and we're done. And then tomorrow we can jump right in at looking at the 3 intermolecular forces. It's really easy section. Okay, so intramolecular, and I'm going to also explain intermolecular. It's very easy. Intra means within. So intramolecular are the attractive forces inside one individual molecule. Intramolecular forces, and I know this can be hard because literally the difference in spelling is 1 letter. It's intra or inter. Intra is covalent and ionic bonding. These are the bonds that hold hydrogen and oxygen together, or sodium and chloride together. We looked at this in sections 3.3 and 3.4. Intramolecular forces hold a molecule together. But now, when you guys drink a glass of water, that glass of water is not full of just one water molecule. A glass of water is full of millions, billions, trillions, like a crazy amount of individual molecules. And these molecules interact with each other and are attracted to each other at different levels. These attractive forces tell us chemical properties. The attractive intermolecular forces, these are the forces between two different molecules. These forces tell us if something will be a solid, liquid, or a gas. And they also give us a hint at the melting and boiling points, which is huge in chemistry 1121 and 2420. So this is something you all need to memorize. And like I'm winking right now. I know you can't see my face. Here's my wink face. Make sure you know this. The stronger the intermolecular forces, the forces between different molecules, the harder it is to make them melt or boil, which means they'll have a higher melting and boiling point. So let me just summarize that again really quickly. Intramolecular forces, these are the bonds that hold atoms together. Intermolecular forces, think of the internet. That's the connection between different computers all over the world. Intermolecular forces are the forces between all of the molecules in a compound, or sorry, in a sample, in a glass, in a beaker, in a swimming pool, in your bedroom. The gases in your bedroom are attracted to each other in some way because of the intermolecular forces. So that's it. That's all I wanted to say. Tomorrow, we are going to look at the three intermolecular forces. Now, I know I say there's 4 types, but we've already done ionic bonding. We did that in section 3.3. We are going to look at the intermolecular forces for covalent compounds. Okay, London dispersion, dipole, and hydrogen. It's really easy, and especially knowing that you guys have your quiz on your next test on D2L, the fact that you can use your notes, this shouldn't be very hard. So guys, I'm done for today. I'm sorry I went a little longer, but if you have any questions, let me know. I'm going to hit stop record. And yeah, let me know if you guys need any help. Do you have any questions? I can stick around.